Today we're going to talk about resistance. Resistance can be thought of as electrical friction. As charges, remember we follow the flow of negative charges, those electrons. As those travel through a conductor, they will lose some of their energy through collisions with other atoms. This is the electrical equivalent of friction. We call this resistance. When these electrons lose their energy, remember, energy is never actually lost. It turns into a different form. So this energy is converted from kinetic energy, moving energy, into heat. Resistance is defined as the ratio of potential difference to current. If we put this in equation form, remember potential difference, capital V, divided by current, capital I, we get the relationship R equals V over I, where R is your resistance, V is your potential difference, and I is your current. This equation is in your reference table on page 4 with the rest of our electricity equations. The units for resistance, if we look at the base units, voltage is your unit for potential difference V, and amps is your unit for current A. You can certainly leave your units this way, or there is a simplified unit called an ohm. R equals V over I is a really important equation we'll use a lot when we study circuits. This is known as Ohm's law. Personally, I like to rearrange this equation so that we get V equals IR. For whatever reason, it's easier for me to remember it this way, and oftentimes you will be asked to use this equation in this form, where you're solving for the potential difference. Sometimes we would call this the potential drop, which we'll learn about in another lesson. Let's do a practice problem. Here's a great place for you to press pause, read the problem, see if you can figure it out on your own, and then check your work. So you have a conductor that's placed in a circuit with a source of 110 volts and has a current of 0.5 amperes. What is the resistance? Here's our given information. Find an equation. We're using this new one, R equals V over I. Substitute, and you get an answer of 220 volts per amp, or 220 ohms. So let's talk about what resistance actually depends on. Resistance is something that we're going to look at in two different ways. We can look at the resistance of a circuit as a whole. So the resistance as those electrons travel through the wires, but we can also look at resistance that comes from the actual type of material that the electrons are traveling through. There's three things that depend on the nature of the material, the size and shape for the cross-sectional area and the length, and the temperature. Let's look at each of these three in a little more detail. These are the three things you need to know that affect the resistance of a material. So firstly, the nature of the material has to do with what it's made out of. So we know that metals are good conductors. For this unit, you should definitely know that silver and copper are the best. How well a substance carries current is known as the substance resistivity. That word resistivity is something you absolutely want to know. The resistivity has its own little symbol. It's a lowercase italicized p. And it's a measure of the substance or the material itself. So for instance, aluminum has its own resistivity. Copper has its own resistivity. And again, that's based on what it's made out of. Resistivity does have a unit. It's measured in ohm meters. On your reference table, page 4, there's a little chart of resistivities for different types of materials. Definitely pull out your reference table, find that, look at it, make note of it. I recommend you circle it or highlight it. A lot of people forget that that is in their reference table. Number 2 here is the size and the shape. So you see two little diagrams here, one on the left, one on the right. The size and the shape of the material is going to affect the resistance, right? Resistance, again, remember, electrical friction. So you can also think of resistance as how easily our charge is going to flow through it. So resistance of an object is directly proportional to its length and inversely proportional to its cross-sectional area. On the left there, you see a short, fat wire. Right? It's very short. It wouldn't take you very much time to crawl through that, and it's fat. So you have a lot of space to move around, and you can easily and quickly get from one side to the other. That has low resistance, easy for you to go through. The diagram on the right, the long, thin wire, has a high resistance. If you were to think about crawling through something like this, you'd have to squeeze through that because it's very, very thin. The diameter is very small. And it's going to take you a while to do so because it's pretty long. The third thing is the temperature. This is something you just have to memorize. Generally for metals, as temperature increases, the resistance will also increase. So hot wires have a high resistance. It's harder for electrons to travel through something that's hot. For nonmetals, this is the opposite. As temperature increases, resistance decreases. Again, this is just something you're going to have to memorize. Putting all of this together, we come up with a second equation to calculate the resistance. Now, this equation is used to calculate the resistance of a material, not the resistance of a whole circuit. That's the key here. So you have R resistance equals resistivity times the length divided by the cross-sectional area. This is also on your reference table, but you need to know when to use it. If you are given a very specific type of material, for instance, if they say a piece of aluminum is used in a circuit, you know you need this equation because it's very specific and you'll need the resistivity of aluminum. You can find that on your reference table. Let's look at a practice example. Again, good idea to pause, try it on your own, and then check your work. So we're going to calculate the resistance of a 20 centimeter long aluminum wire with a cross section of 1 times 10 to the negative 3 meters squared. And this is at 20 degrees Celsius. You'll notice all of the resistivities given to you in your reference table are at 20 degrees Celsius. These are the only ones that we will come across. So here's our given information. Take note, you do need to convert centimeters to meters. You will also need your reference table for the resistivity of aluminum. Right? Again, it was very specific in the question, the type of material, so you have to go to your reference table to find that. We're using this new equation, substitute, and you should get an answer of 5.64 times 10 to the negative 6 ohms. So a resistor itself, this is something we did talk about in class together. Resistor is simply a piece of wire that has a non-negligible resistance, right? So it has a resistance. It's not something that we can neglect. It could be a wire, so wire does certainly have some sort of resistance, but it could also be an actual device, something like a light bulb, a hairdryer, a blender, could even be your cell phone, right? A device that's going to use the energy of those electrons. So it's going to take that kinetic energy that the electrons have, or the electrical energy that those electrons are going to carry, and convert it. Here's what resistors actually look like. Right? There's a way to read how much resistance each of those has, depending on the color bands around them. We're not going to get into that, but if you're into engineering and electricity and you are thinking of becoming an electrician, that's something you'll learn to do. On that note, if you are into engineering and electrical work, you may have heard this term a load instead of a resistor. Right? Electricians refer to loads instead of using the word resistor, and that is just something that converts electrical potential energy into mechanical energy, heat, or light. The symbol for a resistor, this is the last thing you need to know about resistance, is this. Looks like kind of like a squiggly line. This symbol is in your reference table as well. When you're asked to draw a schematic diagram and you have a resistor in there, this is what you'll need to use. So that's really it for resistance. There's one last thing I want to add at the end of this, and that's talking about conservation of charge, which is something that we did talk about when we talked about electrostatics. We know that charge is conserved, right? If you take 10 electrons from rabbit fur, those 10 electrons get transferred to the rubber rod. And we know that charge has to do with current because current is flowing charges. So since charge is conserved, current must also be conserved, which means that the current flowing into a specific point must equal all the current that's flowing out of that specific point. So this is where we come up with junctions. So in the example here, you see 2 amps of current coming down from the left and 4 amps of current coming up from the left. Those two are going to meet, and then they're going to travel as one where you see that red arrow. So conservation, we're going to add those together, and all of that current is going to travel through that red arrow. So 2 plus 4 gives us 6 amps of current traveling off to the right. Let's look at another one. So here you see 23 amps of current coming down from the top. It gets to a junction, and you see those red arrows are where the current is going to leave the junction. So 8 amps goes off to the left. Can you figure out how much current will go off to the right? You should get 15 amps, right? Conservation. So all the current coming down to that point will equal all the current leaving that point. Part of it goes to the left, part of it goes to the right, but 8 plus 15 gives you 23. Here's the last one, a little harder. See if you can figure out how much current is coming in from the right. So you'll notice in these, I've color-coded them. So all the black arrows and the black values are current coming into the junction. And the red arrows and the red values of current are all the current that's leaving the junction. So when you analyze this one, you should get 4 amps of current coming in.